Okay, thanks for coming on this very difficult Friday morning. My name is Jeremy Mikola. I work with MongoDB in in the New York office, and this is an unlikely topic for me. I've not worked much with React, apart from working on some features and pull requests in the last 9 or so months. So I'll get into that in a second. But I've worked with Symfony and Igor for a number of years, and so I definitely have an interest in the project. And so today we're going to talk about, I'm just going to introduce the concept of just asynchronous programming, and then also with respect to PHP and React. And just before we get into it, how many people have worked with React before? Perfect. So this is going to be more introductory. And there's maybe 4 or 5 code examples. Some of them are unfortunately dense, but they all do fit on the slides, so it'll be just 1 page at a time. So by the end of it, hopefully you'll just have a working knowledge of how to start using React and some of the things that you could apply it for in your company. So I will start with the contrived example for just creating a web server, which is a good use of. So anything with an asynchronous, where we're working with any asynchronous programming, it's usually comes down to working with input and output, because that's the things that we can do concurrently. So many people are familiar with Node.js. Yes. How many people have actually used that? So you're familiar with using callbacks and events and things. So this is an example of a simple web server in Node.js. Hopefully that's large enough. Yeah. So it starts out, we just import the HTTP, it has a server, and then we define some events. When HTTP connections come in, we basically run our callback, and then it's just like Symfony's request response, except we define it entirely event-driven. And so the benefit here is that our servers can then, with one server when many events come in, and we can process multiple responses and requests at the same time. And if we look at what this might look like in Python, also using asynchronous design, so it's event-driven here. And this is using the twisted framework. So it's defined a little bit differently than Node.js, so we don't use anonymous functions. But we basically make our controller, and we register this with the asynchronous framework. So every time a GET request comes in this case we're not doing any routing here. So we would run this page. A leaf says there's nothing below me, and we're just putting back hello world. And so we register this similar to Node.js. We basically start the loop, which in this case is the site, and then we say we're going to listen on a certain port here. So the differences here from what we're used to in PHP is we're now the web server. There is no fast CGI or FPM or anything between us and the web server. Our application is doing the listening itself. And so it's possible we could just do this with straight PHP. So I'll take an example there. And this is, how many people have used the stream functions in PHP? That's good. So there's quite a lot. So streams in PHP we have different ways to work with I/O in PHP. And before streams were sockets, which are just the file descriptors. And then still very old, all in PHP 5, but we have stream resources. And with this, we have a lot more functionality in later versions of PHP to work with these extra functions that make a socket server in just essentially 2 lines of code aside from the I/O here. So what we do in the first line here is we create a socket server which gives us back this resource. And the resource is bound to whatever, so we're listening on the local host and this port. And then we can pull that socket and end up getting, every time new connections come in, we can use that socket to get the new connection as another socket. And so here we're just going to loop over that, and every time someone connects, we just go and we write out to the user. So does anyone see a difference between with this and what we saw in Node.js and Python? Yeah? No concurrency, right. So in this case, there's no callbacks happening, there's no events happening here. We just have this while loop. So in the middle of processing one request, let's say maybe it's a slow connection or the outgoing network is blocked for some reason. So this is going to slow down the amount of other requests that we can handle. And so this is a case of there's blocking I/O happening. So we focus on this stream socket accept. So this is the thing that actually blocks here, and we're using -1. The first number is the socket resource. Is the server resource that we create on the first line, and the second number is the timeout. And we have two approaches here. We could use a timeout of 0, which would be like check immediately and see if there's a connection incoming and answer it. Or we can use a timeout of maybe like 3 or 4 seconds or 1 second. But the problem there is if nobody comes in that second, then the script would end because the while loop would close. And so the alternative here is just to wait forever until new sockets come in. But then there's the issue of we might get stuck processing something and we have no concurrency. So to visualize this, of why this blocking I/O is a problem, just to go through a few diagrams here. So in this case, this is us in PHP processing everything serially. And so the I/O comes in, and then we have a CPU. That's our while loop, basically doing whatever logic. So we had very little logic there, but maybe this is in a real web server, you'd be rendering your templates or running your controllers and things like that. And in the time when we have the I/O, this is when the CPU is idling. So theoretically, this is time where we could be doing some other task. And within PHP, we're single-threaded. So if our PHP script is just waiting on something, then we know those resources are just being wasted. So this is the synchronous approach, but it's also very easy to write the code for this. So it was very straightforward to look at the while loop and see what was going on. But there's no parallelization, and we're being inefficient with how we're using our resources here. And the other thing I'll mention is the blocks here are really not drawn to scale. So usually, especially in a web server application, and one of the reasons why Tornado and Node.js can be so performant is that the CPU time is usually going to be very small, and your I/O time is going to be much larger. And a few days ago, I asked, I didn't get any responses, but I was looking for a picture of the Symfony profiler, and hopefully to see when you have the timeline of how much time is spent. One of the things I remember at OpenSky was if we were in development mode and we weren't caching, the time spent querying the database or talking with other external systems was the majority of our controller time was being spent on this I/O with some external system. And so the takeaway here is I/O is very slow. So if we can do something and parallelize so that when one piece is waiting for I/O, and that's the operating system will tell us when to continue. If we could have PHP do other things in that time, then we can get more concurrency and be more efficient. And so to go back, this is a table that has floated around the internet probably for the last 10 years, but it's titled under these are numbers that every programmer should know. And so these are latencies ranging from, at the processor level, how long it takes to get a register of memory or run a single assembly instruction to pull in things, and that's maybe the first four or so lines. And then we have accessing memory, and so those are on the scale of nanoseconds. So maybe 100 nanoseconds to access in RAM, and then to access the registers on the processor, fractions of a nanosecond. And then beyond this, once we start getting into networks and then disks, and then transmitting packets across the oceans and even on fiber networks, things get orders of magnitude much slower. And so it's the network and disk that to focus on, because these are typically in our application, these are the things where we're doing I/O. So on a database server, we might be accessing, we might do a query very quickly. It goes to the index in memory. So good, that's maybe a few hundred nanoseconds. But then it has to access the data that's actually on disk, and maybe it's not in memory yet. So now we do the disk seek, and all of a sudden now we're into the milliseconds range and coming closer to a fraction of a second. And even worse, when we're doing disk I/O, we're waiting on some other network resource. Maybe within the same data center, it could be much quicker. But if you're in maybe using some cloud services in your backend in your controller, then there's more waiting to be done. And so when we apply these, when we consider these latencies, and these are the numbers have not the earlier numbers have changed a lot, but the things like disk seeks and round trips on networks is pretty consistent in the last few years. But you have another issue that's been discussed for the last decade, and this is a quote from 2001. So this put things in perspective here of 1 gigahertz computer. So at the time, going 10 years ago, there were the FTP sites where you could download things, and it was impressive if you could have 10,000 clients at a time. that was not as common, especially for a lot of web services. And so this, the person that came up with this, his last name is Kegel. His reasoning was that if we have all these resources on the computer and all this RAM and all this network bandwidth, and that should be enough to handle individual clients, because they really just need to go download a file, and the CPU really just has to read from disk and then shuffle the bytes over. So we shouldn't need a lot of resources, we shouldn't need a lot of RAM to do this, so it should be easy to scale out for many users. And we'll see this is true today. These are problems that things like Nginx and Node.js have solved, because you have these small machines that can serve. The last blog post when I was researching the slides was some Node.js guy said, oh, I did 250,000 connections concurrently. And then it was a few weeks later, after he addressed all the comments in the post, he said, oh, I hit 1 million connections. And he did a little fidgeting in the Node.js source to remove some limits, but the point was he was able to do that on his hardware. And it took many more Amazon machines to actually simulate the incoming traffic to his one server that supported that. So what are the approaches that we can solve to improve our concurrency in programming? So the first one, I think, whether you've maybe not had the displeasure of using this in PHP, but you probably are familiar with the term, is the use threading. And so this is something that would be much easier in Java or C++, or even in Python. We have, when threading, your single process is divided up into multiple threads of concurrency, and so you each have, it's like having 3 different processes, but they're sharing the same memory space. And in this case, if each thread was responsible for its I.O., we don't really care if it blocks, because the first thread could say, okay, I'm blocking. When I'm ready, I'll go and I'll reply and use my CPU. And meanwhile, the other thread is blocking for its own amount of time, and they're independent of each other. So here we could have the CPU basically getting used as it needs to after each I.O. stream. And so the trade-off here is it's very expensive for the operating system and the computer to shuffle between threads, so maybe not with a few, but we look at having maybe thousands of threads, or in a large, using like threaded Apache with many, many connections. This can get a lot less scalable at that end. And additionally, we can consider, even if you didn't want to do threading, maybe you replace this and just have a pool of processes. So something like the way workers, FPM workers work, we have a pool of processes that they all run PHP, and we have about 40 or 100 of them running, and the web server can just use them independently. But the other approach is to use non-blocking I.O. And so this is what Node.js does, is what Tornado does, and we'll see this is what React tries to do in PHP. So this is all event-driven, and so we have, this is all happening in one chain of concurrency, so we have the CPU usage cannot overlap because it's in the same process. And so here we can use the operating system to basically issue a call on the I.O. block and ask the operating system, are these I.O. blocks ready to be read to, or sorry, be read from or written to? And we could, because the operating system implements that, it's very cheap for the CPU instruction to happen. And so we could basically say, let me check it immediately, or I want to wait, I'll wait up to X number of seconds or milliseconds. And so the system call for that is called the select function. We'll take a look at that in a bit. But this isn't just about socket I.O. It could also apply to if I'm reading from disk. And what is the, so one of the things in MongoDB that we're trying to optimize is that when you look for something on disk, ideally it's been accessed before and it's in memory. Because we map the files on disk and we have them in memory. So just like we have select for socket I.O., which is you could pull the sockets and see, can I read from these without blocking? The same thing if for reading from disk, you can check if the disk has been paged into memory. And so that's the mincore function in Linux. So that's the equivalent of, I don't want to access this bit of memory and then find out it has to go to this slow storage medium. I'd like it to already be there. And then if it's with select, if it's not ready, then you can go do something else, come back, check later. And then same thing with mincore. If it's not been paged into memory, then I can maybe go have some other process go try and load it from disk and not do the blocking. And then I can free my event loop can go do some other tasks and come back later when it's ready. And so a good illustration of non-blocking I.O. is if we compare how Nginx works with Apache. So Apache implements either a threaded design or a worker design, depending which you're using. Then Nginx goes the other process of a much more lightweight web server, but it's also very highly event-driven. And so it reaches a lot of performance levels that rivals Apache, while also having simpler code base and basically being the underdog and more like Node.js compared to a large Java application. And so there's many tools within PHP that we can use to either create any kind of like polling, or do concurrency by whether we have actual threads at our disposal with the pthreads extension that's in core. And we also have plenty of very confusing functions to use if you want to launch other processes from PHP and have your main PHP process kind of be the coordinator and launch a bunch of processes which will be your workers, and then give them tasks to do and communicate with them through either a socket or some other mechanism. And then if we're working with sockets themselves, we have the stream APIs, and we have the older socket APIs. And then even using things like curl, curl has an extension so that we can do multiple curl requests and multiple HTTP requests asynchronously and have them not block each other. The problem here is that none of these APIs are very pleasant to use. So this is the issues with proc open and process PC NTL fork and everything is the reason we have like the Symfony process component, because we wanted something much more friendly to use instead of using these raw functions that also aren't very testable. But the ones that I want to consider today are the stream select and stream set blocking, and these are going to be what React uses for its loop. So before we do that, I just want to mention a little bit. So I mentioned the min_core function, I mentioned the select function earlier. So these go back to, and in the Jeopardy yesterday I mentioned, well, what is the language that a lot of the PHP functions are borrowed from? So it goes back to C. And so on Linux or Unix, if you've never used man pages, you basically use those and look up either commands on your system, or in man2 we have the group of all the system C functions for the operating system. And so select is one of the oldest, and there's another variety. It might be have pselect on your system. And so these are, as it states, for synchronous I/O multiplexing. So it means that we can have multiple I/O streams, and multiplexing, we're basically going to track and poll many of them at a time. And then select basically does the polling. It may do if we want to wait a certain amount of time, it would do the blocking for us. And so the benefit here is that we can work with many, many streams at once. So this is what Node.js would use with thousands and thousands of connections at a time. And it defers all this load to the operating system, which handles this much more efficiently than we could in our own software. And so an example of polling I/O in PHP, in this case, we have in selects API, you would have an array, or in C a different structure of streams that you want to read from, and then another of streams that you want to write from, and maybe they appear in both because you want to. Maybe it's a bidirectional stream that you can read and write. But we have separate arrays for the ones that we want to examine for each. So reading, writing, and then things we want to check if there's exceptions, so maybe some errors on the stream. And with stream select, you pass in the arrays. In this case, they're passed by reference. So we can't just pass in an empty array literal. I would have to actually create the variables. And then towards the end, we have the timeout value, which is similar to what we saw before when we did socket accept server in the very first slide. And so stream select is going to return basically the number of sockets from all the across all the arrays. It'll return the number of ones that are actually have activity that we cared to check for. And so the next logical thing to do is then loop through these arrays, and basically after stream select returns, the arrays come in, that's what we were looking for, and they get modified by reference, and then they're just the results of the sockets that have activity. So we iterate, we'll just be looking at the ones of actual interest. And then inside we'll do whatever processing. So the for each for the reading, we might do the fread or whatever the read socket receive operation might be, and likewise for writing we do the fputs or whatever that might be. And the other thing to consider here is with the timeout. So we have, just like the very early example, we have the ability to block indefinitely, which is probably a problem if we want to be able to do other things in the meantime, if there's no I/O to be done. Additionally, we could use 0 to just say poll immediately and return immediately. And using a 0 poll, which basically would return back to the CPU immediately, this would be bad if we did this in a very tight loop. Because it'd be essentially like running, if there's no I/O activity and we're just constantly calling the stream select function as fast as we can, it's like doing a for loop that does nothing, or a while true, which is open close brace. And if you run that, your PHP script probably balloons and uses full CPU because there's no sleeping, there's no waiting to be done. So it's probably important, if we're going to have any way to do things concurrently, we probably want to wait at least for fractions of a second so that we're not slamming the CPU. And we actually let other things run in between. And so this brings us to the event loop. So where we're going to be doing our stream select and the polling is going to happen in the context of this loop in our application. And then, so using an event loop in these situations reminded me of doing like game or OpenGL programming back in college, where you basically run those applications. The games, when you load up a game, you go in, you take input, and it's the game program's responsibility to, as long as you're in there, watch the keyboard for input, watch the mouse cursor for input, go through the menus, go through and play StarCraft or what have you. And it's basically polling for your input as the user until you exit the program. And it's doing that in a loop. So in between the loop of actually polling for your input, it needs to draw the screen, play the sound effects, do the network communication. And so the event loop in this case is very similar. The things that we're tracking in this, instead of keyboard input and graphics and network like that, the two main concepts are the timers. So we could have timers for different events. These might be things that we run one time. We schedule, I want to run some callback function 5 seconds from now. Or maybe it's something I want to do periodically. Every second I want this callback function to run. And then timers can also be canceled. And additionally to that, we have the streams, and these are essentially the sockets that we're either reading or writing to. And in this case, each loop iteration ticks over, so we consider that like a clock tick. And this is analogous to a CPU, goes through its instructions. Every instruction is a tick in the CPU. And then each tick, we're going to execute whatever timers are ready to be executed. So whatever has been scheduled, and it should be running now immediately, we'll run that. Additionally, we can pull the I/O. And that might be pulling it instantaneously if we know there's things to do immediately after, or it might be blocking. So the polling timeout, we can calculate how long we can actually wait for. So in this case, an example of that, if I have several streams, several I/O streams, and then I know my next scheduled timer, so the next code that I actually have to call back, the next time that's going to run is 5 seconds from now. So I know either something happens, there's some I/O, and then we're going to run some on new connection or on data is available to read. We're going to call those event handlers. Or I know in 5 seconds I have to run a timer. So I can allow the polling to block for 5 seconds. And this will allow me to sleep and be more efficient with the CPU. And I know that in those 5 seconds, if I have I/O, it's going to return immediately. But if there's no I/O, I have nothing else to do, so let me just wait and monitor the sockets for 5 seconds. Does that make sense to everybody? So basically, we know how long we're allowed to wait safely. And so in this case, blocking is okay if we know there's nothing else to do. And the loop should naturally end, just like in a game program. If there's no more input, there's no more sockets to read, there's no more input-output, there's nothing to do, so it'll just end. So the loop starts, and it's just going to continue going ad infinitum, and then when it knows that there's nothing to do, we can return, and the program would naturally end. And Node.js really works the same way, although a lot of times the way we use event loops is to have these persistent servers. We want to have the web server running forever. And so this brings us to React, which is, to quote the tagline, event-driven asynchronous I/O for PHP. And to revisit the old example of the hello world where we used the one that was blocking with socket accept server and socket pull. In this case, if we use some of the React functions at our disposal here, let me just make it a little bigger on my screen so I can see this. So we create this event loop, and we use a factory because we'll see React has a number of different loop models that we can use. Some of them use, one is pure PHP, and some of them use some C extensions. And then inside that, we would create a server. And this is similar to what we did in Node.js. We created the HTTP server, and then from there. So in React, we have the socket server, which is a generic thing for generic for a network server over TCP. So on top of that layer, then we construct the HTTP server. And that uses the Guzzle library to do all the actual parsing. So in the HTTP server, we really don't have to do any of the implementing of the complicated HTTP stuff. And as you'll see in React doesn't implement a lot of the complicated HTTP stuff. We don't have keep alive and some of the other features. But it's useful for a lot of general cases. I would say SSL is also something that is down the line to be implemented. But this looks really analogous to the Node.js example. So the HTTP server is connected to the event loop through the server, through the socket server. And on a request that comes in, we will run this callback function. And so this is where it's very analogous to the way Symfony works in our main controller, where we have response equals handle request. So on a request, we have this request object and response object. the request is already populated for us. That's what Guzzle parsed out of the incoming socket data, and it's our job to populate the response. And there's nothing to return here. We basically we modify it and fill in the data that we need, and then we'll rely on the HTTP server and the socket server objects to actually put this back across the wire. And so in this case, I'm just going to write out hello world, just 11 bytes. And after defining my callback, the next thing I'm going to tell my socket server that I want to listen on this particular port, just like we did with Node.js, and then start the loop and let my PHP script continue running forever until it either runs out of memory because I have circular references with Doctrine, or I'm just going to have it wait until there's no more socket activity. So maybe if the socket ends up closing or something. But left undisturbed, this should run forever and be there to answer requests. And so the benefit here is that while we're doing request response, while I'm running that response out to the socket or I'm reading the request, or rather by network driver, there's the request coming in and it's not actually available to be reading, PHP can go and maybe execute this callback. It could actually run the 2 lines inside for another function. So it's much more concurrency is happening here. Even though it's not as good as we have with Node.js and V8, which is designed completely for concurrency. So the design pattern, and I promise there's only one of these in the entire presentation, that React implements, and the namesake of the project is the Reactor Pattern. And so this is arguably the most popular pattern for asynchronous design. So it does not involve any nuclear materials, but it consists of 4 concepts here. We have resources, and these are basically, in this case, the streams that we care about. We have a dispatcher, which is what we need to do the events. So on a request, so we saw there was request was the HTTP server's main event that we listened to, and there's things for closing. At a socket server, the events might look like connection, and it's just vague like that. So depending on on a stream, we might have, the event might be there's stuff to read, or it's available for writing. The demultiplexer is basically our polling loop. So this is what monitors our resources. And then when we see that there's I/O, we could either do I/O or that we can read something, we would use the dispatcher to notify our handlers. And the request handlers, in our case, are going to be probably our callback functions, which, thanks to PHP, we could use anonymous functions here instead of creating a bunch of global functions. And I will say there's a less common and probably more efficient pattern called proactor. So reactor means we do the monitoring and then we do the dispatching. And the dispatching is actually done synchronously. So when we run our callback, the event loop has to actually go execute that function and have it return something. So that is the point where that is blocking at least. So in our callback function, if we did something very CPU intensive, or in my on request callback I said sleep for 10, I would block the entire application. So a different pattern is the proactor, and this makes that actual delegating to the resource handlers and the callbacks, that part would be asynchronous as well. And there aren't many libraries that implement this, but one of the most popular ones is in C++, the Boost asynchronous I/O library does this pattern. And my take on React, it's definitely probably harder to use. It's not something that Node.js implements, but it is probably the more performant of the two. So a look at React's stack. So we start with the event loop, which we looked at earlier in raw PHP. And underneath the event loop, we need to work with events. So we need an event dispatcher. Symfonies would be nice, but Igor went ahead and created a library called Eveniment. I hope I'm pronouncing that right. And so that is our event emitter, and it basically implements the same kind of on and then the string event name and a callback. So the same API that we'd find in Node.js. And there's certainly no requirement to do that, but it makes it consistent for other asynchronous programming experiences. And then on top of the event loop, we have streams. So these are the PHP resources. And earlier we saw the event loop can actually work with the raw PHP streams. But it'd be nice, since we're going to be doing things with events, we will have stream wrapper objects that will also be able to have listeners and things attached to them. But really, they're just wrapping a PHP stream resource. And then above that, we'll have the socket. So this is where the socket server class lives. And then above that is where we do our services. And so we have the HTTP server. HTTP by default is the server. There's also a client component. And one of the first instances we'll see of having to kind of implement things ourselves because things are getting complicated, is in PHP when you're connecting to a web server, and the first thing you need to do is resolve the domain name. And if you use PHP's internal functions, which would be like get host by name or the internal resolution that the PHP engine will do, that will block on the query to the DNS server. So one of the first things that had to be implemented was a asynchronous DNS server, which is all implemented in PHP. And so you could imagine there's a lot of byte packing and unpacking and a lot of binary stuff going on in that component. So this DNS component will get used by both the HTTP client and, well, probably just the HTTP client. I don't think the server needs it. And then on top of this, this is where all the other services are coming into play, and they're all at the same level. These don't necessarily depend on PHP. Some of them might. There's the Redis for async. There's a PHP extension for that, so there's a Redis component to work with Redis asynchronously. Stomp is a way to communicate between processes. There's an API for that. There's ZeroMQ. Someone has an IRC project. WebSockets is perhaps the most well-known, maybe more than React itself. The project there, so Igor and Chris Bowden both work on React. Chris Bowden also has a Ratchet WebSocket library called Ratchet, if anyone's familiar with that or using that. And then we keep building things on here. There's something to control remote aerial drone helicopters. There's Berge, Henry Burgess created the dnode interface, which is another thing for communicating between processes. And there's other things as well. And something that I worked on last summer, it was at the level under these things, was to work with child processes. And I'll get into that a little bit later. But this is, think of somewhat like Symfony's process component. But the problem I had with Symfony's process component is it runs the process and collects its output on standard out and then gives it back to you. But while it's doing that, it's blocking while reading the standard out of that process. So with React, I basically wanted to be able to fork another process and then wrap its things in streams so I could watch and wait if there is actually stuff to be read or not, and put data into the process and backwards without actually blocking. So that was the logic behind that. And so the event loop in React, we can add, remove streams to it. So basically say that we want to start tracking a stream. So when a connection comes in, first thing we're going to do is start tracking it. After we accept the socket, and now we have this stream resource, we'll start tracking. And then we might have the timers that I mentioned earlier. And then I mentioned also that we use the factory. There's multiple implementations of the event loop that we might use. So there's the default one. The goal was to also have React be able to work just in normal PHP. So that's the stream select loop. And this uses the stream select function and a bunch of other PHP code. And its event loop basically looks like it does the polling. It checks if there's timers. It calculates how long it needs to sleep. It's pretty straightforward. And then there's two extensions in PHP to do asynchronous programming. They're both the C extensions, and that are libevent and then libev. Libev is what Node.js originally used. It was only for, I think, Linux and BSD, so Mac. Libuv is the cross-platform version, so it adds support for all the Windows users, which was more important to Node.js. The PHP extension for that, though, is experimental. So it's not supported in React yet. But the main difference between libevent and ev is libev is object-based and actually has namespaces. And libevent is a bunch of top-level global functions like we're used to in old-style PHP. And so what the event loop, in this example, we're going to use the event loop before we even do anything with the stream or sockets inside React. This is just going to use the raw streams that we saw from the very first example. So stream socket server, I create this resource, which then in that case, I'm listening on that port, and from there I could accept sockets. And with the loop, I will basically add this stream resource. So it doesn't necessarily, we don't have to necessarily add React streams, we can add raw PHP streams. And the first thing we do when I add the restream is it takes one callback. So we're not using React streams, so there is no event names for the stream. So it's basically when there's read activity, this function will run. So there is no specific on data or on close action here. But the first thing we do if there's read activity on our socket server is we'll accept it and we'll get that new connection back. I'm just going to create my familiar HTTP response here. And then after that, I will add the loop to the, the stream as a writable stream to the loop, so register with that so that it will pull it and see, well, when's the next time I can write to this stream without blocking, just like it did for the reading. And then from there, this callback might have to run multiple times, so I'm going to try to write everything, but then I also have to check. I tried to write 50 bytes, but I need to check if all 50 were written or just 30. And so if I wrote everything, I can clean up and close everything down. Otherwise, I'm just going to advance in the data using substring so that my callback is going to run again and I'll just write the remaining bytes. So realistically, this probably won't take more than one callback because it's only 50 bytes. But if you imagine you were sending a large web response, you might only be able to write, say, 50, 100 kilobytes at a time, and then you might have to wait until the data has been read, and then your operating system says, okay, you can write to this socket again. There's space in the buffer. And then stream set blocking, which is the function we're using at the top, is still very important. So that basically tells us when we're doing the actual reading and writing on the raw stream resource, is that allowed to block at all? And the reason that we need to say that no, it's not allowed to block is because we might do the pull loop and we might say, yes, you can write to the stream, or yes, you can read from this. But if we start, just because something's available to read, if we tried to go and read, say 100 bytes and there were actually only 50 available, we would block until the next 50 became available. So by using set stream blocking, we could basically say I'm going to read, but then I might try and read this much, but if only this much is available, then I want to return immediately. And that's fine because we're also tracking how many bytes, in this case of writing, how many bytes did we actually write. So we prefer to not block at all and then just keep track and knowing if we have to schedule this again. And so the layer above this, because it's not fun to work with those raw streams and we'd like to have events on these things and such, is to have the stream component. And so the goal of this in React is to wrap those raw PHP resources and have a nice object-oriented API. And we still register these with the event loop the same way. And the streams can be readable or writable. In the case of most cases, in case of a socket, the stream is actually bidirectional. So you might read to it and write to it for one accepted connection. And internally, React is going to use a buffer both for the reading and the writing, as well as whatever the operating system, certainly at the networking layer, has its own buffer. So just most of the slides of this format are really just summarizing what the interfaces are, and I'll cover any of the important details. But a readable stream, we basically check, is it readable? So is there actually something available here? I can pause it and resume, which is basically register it with the event loop or not, or either register it or take it back out, which means that if it's paused, no callbacks will run on it because we won't be checking if it's able to be used. And then to construct chain streams together, we can do piping, which is just like piping on Unix command line. We do run command and then you pipe it, and to another command, you're basically connecting standard output of the first command to the standard input of another. So we can do that with streams, and so whenever a stream if we pipe one stream to another, whenever one stream has output, I immediately want React to push it into the next stream as input. And then lastly, we can close things. The events that we get, so the benefit here of registering ourselves with a loop and also being a stream class here is that we have events that we can listen on. So using on the stream, we do arrow on and the event name. So data will tell us that yes, there's data to read. And then there's the events that are pretty common are when end or close, or when things have completed, or if there's an error condition. But the most important one here, and the one that you most likely use, is the data event, which is just on the data. Then there's a callback function, which will get the data that can be read. So the writable stream is the flip side of this, and basically mirrors it, except instead of a pause and resume method, and the events are a little bit different, we basically instead of responding to a write event, which wouldn't make sense, we actually proactively would decide to send data into the writable stream, either by write or by end. End would say, write this data and then close it. I might pass nothing, in which case it's just like calling close. And the event of interest here is, one, we have an event that tells us something has been piped into us, if we want to log that or do something. Drain is the event that tells us that we previously were full, so we weren't able to write. But I've been drained now, which means I'm available for writing again. So if there's another case where you were calling write and it would end up possibly blocking, and so we would avoid that and just return immediately. You wouldn't get to write everything. but you would then maybe wait for a drain event, and that would tell you when it's okay to retry and deliver the rest of the payload. And so to visualize these, and I spent way too much time on all these, next 5 slides last night, with streams to visualize readable and writable. If Mario is a bunch of bytes running between, we have, and I know Marco really appreciates this, the readable pipe, basically, data can leave that, we can read from the readable and then push it into the writable stream. And then there's some classes, since we have these basic readable, we have a readable class and a writable class, we can have a composite stream class, which basically internally has a readable and a writable. So in this case, we take a readable, we take a writable, we construct them together, and now we can have data flow right through them. And then additionally, on top of this, we have a through stream, which is very similar to composite, except it also has this filter function. And every time data passes from one to the other, we basically can call a filter function. By default, it does nothing, but logically, you would probably extend through stream and then override the filter method and maybe concatenate the word cape onto every bit of bytes that come through. I don't know, whatever you would like to do. But you can change the data in any respect as it from the input to the, sorry, from when it's written to when it's read on the other side. And lastly, we have the concept of a buffered sync. And this is useful if you've had enough asynchronous programming and you just like to say, I would like to read all this, I don't know when all the data is going to be written to me, but I just want a string on the way out. That's all I care about. I don't want to deal with these event handlers or anything like this. So I would just like that question mark box, and I don't care how many Marios have to go in or how long it takes. So this converts something that's writable into a promise. And is anyone familiar with promises, or maybe from using jQuery? Okay. I'm going to take a quick segue, and we are going to talk about promises for a few slides. So the main benefit of promises, or sorry, the practical benefit, and not necessarily the purpose of them, is to avoid, how many people have dealt with callback hell? Of just having easily in Node.js, when I first used it many years ago, you have a callback function, and then that has to do something asynchronously. And so from that asynchronous function, that you have another callback of the result from there, and then another callback. And so your code kind of looks like this, and then you have all the closing parentheses, closing parentheses, closing parentheses. And the problem is, in the very middle of that shape, you throw an exception, or how do you test this? But you throw an exception or something, and you're trying to debug into there, and you just go, and then you go outside for coffee because you don't want to think about it. So promises allow us to have the asynchronous functions return something immediately, which is great because now we can treat it like it's like, what is the benefit of synchronous code is that I call a function and it returns something immediately, or it throws an exception immediately. But I have a result to work with. So promises are is basically a concept, and in any library that implements them, it's basically an object that says, this is an object, there may not be a value in here now, but you hold on to this, and there may be a value here later. So the benefit here is that we no longer have to, we can basically call an asynchronous function and get something back immediately, and then off of that might return a promise. We can then say, okay, when that returns, I'll attach another callback. And we can, instead of defining things like this, we could just define things one level in at a time, and each callback function is pretty straightforward to visualize. We'll go through 2 examples here, but the main benefit that this provides is it allows our synchronous functions, which are the normal things we're used to directly correspond with an asynchronous function, because the concept of I call this, it returns back something is preserved. In React, there's a separate library in the React project called Promises, and it implements, there's a common JS specification that there's a bunch of JavaScript implementations of promises. Okay, so the first case is a deferred. So a deferred object basically represents that computation, and the deferred is what's going to be used internally inside your async function. But deferred is a factory for a promise. And so this internally keeps a promise, and the promise might end up being resolved, which means that some result came in there, or it gets rejected. Maybe there was an exception. So this is the producer, and promises basically consume the returned result. And so the promise is the placeholder for the deferred computation. And so they basically have that then method, and this is what you can use to construct a chain of things. So you call one async function, and then you say then, and you specify various callbacks if the promise succeeds, if it fails, if there was some error. And the next callback would be returned in this case. And the important thing is that then basically builds promises will just wrap each other. And the example case of this in action is using the DNS resolver. So we create our loop, we create our DNS factory, and we basically, our DNS client, we say we're going to go connect to Google's DNS server. And DNS, I say I want to resolve the first argument, which I'm going to pass in the conference website. And resolve is going to immediately return, so I don't have to say resolve this website, comma, here's a callback. I could say resolve is going to return something, it's going to be a promise. So I could say then, once this promise evaluates something, I'm going to say on the success case, I want to echo out the host. On the failure case, I'm going to say there's an error. And then I could just run this. And let's say that the resolution returned, it was the result of some other asynchronous thing. So I can chain the then commands, and my code shape is now much more flat and manageable instead of going in and out. And it also gives me the ability to handle errors meaningfully. So in exception, if an exception happens deep within that chain, instead of it being thrown all the way up and then me trying to configure out what the stacks are, with the promises, it'll ultimately get surfaced as a rejected promise at the top level. So I could resolve this and get the host to return back. And I threw in Warsaw for 2014. It also happened to be the same address. So I don't know if that means that we're having the conference here next year. I'm going to go back to the main content here, but the reading, if you Google, you're missing the point of promises. It's also in the React promises. It's linked in the documentation. It's a good write-up on what is really the benefit of promises and the authors complaining about how jQuery does it versus all these other libraries. But this is a very good read if you're curious. Okay, so back to React. So we have the socket, and this abstracts the stream socket server. So we no longer have to call that raw PHP function. We now have a testable class that we can use. And the connections here are going to be readable and writable, just like the raw PHP streams. And so once the socket server is a resource, we accept an incoming connection. That's now something that we can read and write to. And socket has both on the client side, we have a connection object, and on the server side, we have the server object. So the socket component does both ends of this. Currently, it's just TCP. There is talk in the React chat room about implementing UDP, which is basically just not having a session, just sending individual bytes across the network. That's something Node.js already supports, and maybe React down the line. But the interface we see on a server, and this is what we've seen in all of our examples, we basically, when we create the server, we ultimately say, I want to start listening on this interface and port. And then get port will basically tell us it's like getting the local name of the socket, and then we can shut things down. The actual magic here is happening with this server is not going to do anything unless we define some event handlers when new connections come in. So the most important thing here is the connection event. And whenever these are accepted, we basically get new streams. And those are going to be, in our case, connection objects. The connection object here, by itself has one method, which is get the remote address. It's just similar, it just gets the socket name. It's just labeled something different. The name has a different context here. But all these other methods, which I faded out, are basically inheriting a readable and writable stream. So connections are just readable, writable streams, but they also have some remote address because they are representing a socket connection. And so the events here are everything that we find on the previous streams. So working with an actual accepted connection versus any other streams in React. So even if you're using child process and you're talking with standard in, standard out of the next process, the events that we're working with are the same. So I can pipe incoming TCP connection into a child process's standard input, and then just have the data from someone telnets into a socket server that I'm running, and I would just like to pass that blindly into another service, which is probably a bad idea, into another process. But React makes it very simple because they're both streams and we can join them and listen on the same events. And so an example of this is TCP Chat, and I just did something bad. Is it still on the screen? Yes, it is. Okay. Actually have to go up and down. Okay, I'm back. Sorry, my view got messed up. So the TCP chat here, after the talk, I think we're running a little bit out of time, but I can go through and talk about this or give a demo outside. We create the socket server, and every time there's a new connection, that incoming connection, we just want to store it in our array. And then every time there's data, if it's to everyone else that's connected to us, not the same user that just posted this incoming data, we just like to write it out to them. So this is like a very, very dumb chat room that you would run from Telnet. So if I had this running on my machine, we could all Telnet in on port 4000. You type something, everyone else that's connected would also see it echoed immediately. But the important thing with React is to avoid blocking. So in all these cases, we're doing pretty similar stuff. Data comes in and we just shoot the data right back out. But you might be tempted to do, if you're making like a HTTP server in React and maybe you want to do a database query. So you will connect to MySQL or connect to MongoDB or Postgres, and immediately there's your first instance of blocking because you're creating that connection. That's not being done asynchronously. And so this is the easiest way to shoot yourself in the foot. There's also maybe just something like doing a file get contents. Okay, maybe it's on the local disk and it'll happen pretty quickly. You don't realize that you're blocking. What if it was on, you're loading it through S3, using S3 : as the stream wrapper in PHP. This could block for any number of time. And while it's blocking inside your callback function, since you're not using the event loop, you're basically locking, the callback is the only thing that's running in for all of PHP. So all the other, you can't do any other I/O, you can't do any other polling or execute other callbacks. So this is a problem. And then the last one, which is easy to miss, is CPU, anything that's CPU intensive. So I don't know how many people remember, it was a Hacker News article called Node.js is Cancer within the last year. And it was a Python developer, he was complaining about, he made some example using Node.js to calculate Fibonacci numbers and run this big recursive function, so it was very CPU intensive. And he said, look, I'm running this and Node.js stops. It locks up the event loop. And so that's a fine example of doing something very CPU intensive. And since there's no I/O to be done there, you're just basically, it could be as simple as in PHP maybe doing a large array search function, or JSON encode or JSON decode and passing in, maybe on the request, the incoming post body of the HTTP request had several megabytes of JSON. And so you call JSON decode to get that into an array. Maybe that ends up taking an actual lot amount of time in PHP. So these are things that you have to watch out for. There's helpful tools to avoid this. So the first is to use inter-process communication. So React has stomp and dnode are meant for basically having separate processes, or maybe other, not even in PHP, dnode can talk to Node.js servers. And basically using this asynchronous API to talk to them and have them do the work offline where you don't care if it blocks. Additionally, using the child process component. So I can, in React, fork another process and have that, I don't care if that blocks. That's similar to if I had a separate thread of control. And I can write something to my child process and have it do that blocking, maybe do the database query, and then send something back to me. And the important thing is my event loop. It may not be the most efficient thing, but at least my event loop in the main React process is not getting blocked. Additionally, we have message queues, so that's what ZeroMQ, and you could also use Redis for this. So having something like a pub sub where you put a message out in the wire, and then you have other listeners are just basically watching for messages in their channel, and then deciding to take action. Maybe those are things on separate machines outside of React. And then the other idea is to use, so in the loop interface, we have this function called nextTick, which basically says, in the next tick, I'd like to run this callback function. And so if we had something like an array search or Fibonacci, instead of just recurring, or instead of doing the full iteration, if we think about how maybe MapReduce works with Hadoop, it runs a little bit of the computations in little isolated chunks, and that way they can be parallelized much better. So with nextTick, if say we had to iterate through 1 million array entries, if every tick of the loop we decided to go through 100 or 10, something that's manageable in PHP, we know it's not going to take forever. I can do that for the first 100, and then next tick I'll do the next 100. And then when that's done, the next tick I'll do another 100. And allowing the ticks to interleave means that in between that we can do the I/O, poll for the I/O, and run the event handlers. So we could do this large array search or this large JSON encoding if we were doing it in pure PHP, and basically decide to pause at certain points to let other things happen in between. And lastly, there's, Dennis only just told me about this yesterday because I don't pay attention to MySQL as much. There's ways to work with MySQL with the MySQL native driver in PHP 5.3 to do MySQL, asynchronous MySQL connections. And so the thing of interest here is MySQL I_poll. and this kind of looks familiar. This is actually something very equivalent to what we saw with select stream. Excuse me, select stream. So with MySQL poll, we can basically read multiple MySQL connections and have this do the same thing where a read will be modified to be, these are all the connections that actually have a query result that you can read. So this is an idea possibly if you're working with Reactor in any kind of asynchronous PHP to look into using this. I think unfortunately other database drivers would need to be specially supported to, this is certainly only MySQL. So other databases would need special asynchronous APIs to be made, kind of rewriting a whole driver. But it's nice that this already exists. It's something to experiment with today. So this is the future of things. And if you would like to play with them, React 0.4 is the next version. That's actually the one with the child process was merged over the summer. And this is the branch. It's still not stable. I think 0.3 is the current stable version. But this will be out soon. I mentioned WebSockets as perhaps the most well-known application of React. And this is from Chris Bowden, if you'd like to look that up. More importantly than WebSockets, does anyone know what's coming next? There are GIF sockets. So this is for having asynchronous communication over the web in browsers that don't support. Most browsers support GIFs. Most browsers do not, I mean, older browsers do not support WebSockets. They don't have the JavaScript API. This actually works in IE6, and this is a stupid animated GIF, but actual WebSockets are basically, we send data as the first frame of an animated GIF, and the browser will just keep waiting for more data if we don't say that's the end of the file. So what we could do in React, or it was actually Alvaro Videla is his last name, Old Sound on Twitter, originally made this in Clojure, and then Igor has too much free time, he ported this to React. We basically send some data as the first frame of the GIF, and then if more data comes in, then we send the next frame of the GIF. And so if you're in some browser, you just have the image there, and data is coming onto your screen. And it just never ends. So you can have a chat room application, basically by having a GIF file and then a form at the bottom. And this is Web 2.0. Someone described this as WebSockets for the 90s. So thank you. This is the join in link, and that is the React website where you can see a bunch of the silly projects that use this. And we'll go outside so the next speaker can get started for questions. But thank you for your time.